Okay, welcome everybody. So in this video, let's now consider how we can use homogeneous coordinates to incorporate translations in with our other transformations in the plane. So if we want to compose, for example, a scaling transformation, a rotation transformation, and a translation, we want to compose all three of these together by multiplying by a single matrix. And so the issue that we've had up until now is that translation was addition. And these first two operations can be represented by matrix multiplication. So how can I compose two matrix multiplications with this translation? Well, we introduce homogeneous coordinates so that translation can be represented as matrix multiplication. And now we can compose these operations by multiplying their corresponding matrices. So for this particular example, if we're considering the following transformations, transformation 1 is a scaling transformation by a factor of 3. So that matrix we saw initially when we were thinking about a map from R2 to R2 had the first column of 3, 0, and the second column of 0, 3. And now, because we're adding homogeneous coordinates, we need to add an additional row and an additional column. And we're going to add all zeros except for in the third column, third row, we have 1. And then we take this rotation matrix. And so now in this case, we're rotating counterclockwise by pi over 2, which is 90-degree rotation counterclockwise. We have our rotation matrix, this 2 by 2 matrix in here. And again, we just add this extra row and this extra column of zeros, except we put a 1 in the third row, third column entry. And then the matrix representation for B, I'll call B this translation to the right by 5 and down by 2 units. We put the plus 5 as the first entry in the third column. The minus 2, the vertical shift, goes in the second entry in the third column, and then we have a 1 as the third entry in the third column. So this rotation matrix, if we evaluate the sines and the cosines at pi over 2, the rotation matrix is a 3 by 3 matrix. The first column is 0, 1, 0. The second column, minus 1, 0, 0. And the third column is 0, 0, 1. And so now, applying these three operations in this particular order, first S, then R, then this translation by matrix B, we can apply this by taking the product of these matrices in the appropriate order. So first multiplying by S, then we multiply that on the left by R, and then finally we multiply that on the left by B. And so taking the product of these three matrices, again, you can either multiply these two first and then multiply by the third one, or you can decide to do the matrix in blue times the matrix in black first, and then multiply on the left by the first matrix. However you want to multiply these three matrices, you should verify that the composite of these three operations would be equivalent to just applying this one matrix, which is the product of B, R, and S, which in this case is a 3 by 3 matrix where the first column is 0, 3, 0, and the second column is minus 3, 0, 0, and the third column is 5, 2, and 1. And again, this matrix came out of taking the product of each of the three individual transformation matrices. And so let's see what effect this is going to have on our triangle on the next slide. Okay, so finally, let's go ahead and show that if we apply these transformations in the appropriate order, one followed by the next, followed by the next, we're going to get the same thing in the end as if we just took the product of the matrices representing each of these transformations and then mapped each vector by the product of those three matrices. So if we were to first scale the triangle by a factor of 3, that would give us this triangle that we have in red. Okay, next we rotate this counterclockwise by 90 degrees by pi over 2. So that takes this triangle that we had in red, and now it gets rotated 90 degrees over here to this blue triangle. And then lastly, we have our translation, which in this case is 5 units to the right, so plus 5 in the x1 direction, minus 2 units in the vertical direction. So every point, for example, this vertex goes 5 to the right, 2 down, and we'll do this for all 3 vertices. And then in the end, we get the final result is this triangle that we have in green. So we could do some transformations and then translate things back to more or less where the triangle started to get scaling and rotations and things like this. So here I took the black triangle, we first did the scale, then we did the rotation, and then we did the translation, and we can check that this is equivalent if we use homogeneous coordinates instead. Then we have, this was the matrix that did all 3 of those transformations at once. So again, we found this matrix by multiplying in the following order. We took the translation, which was B. We took the rotation, which was R. And we took the scaling, which was S. So if we first apply S, we first took S, we multiplied it on the left by R, and then multiplied that on the left by B. And that's where this matrix 0, 3, 0, minus 3, 0, 0, 5, 2, 1 came from. So we apply this matrix to the point at 1, 1, 1, and that's going to tell us, for example, where the point at 1, 1. So it's just the first 2 coordinates that we're interested in when we want to plot this result. So the point at 1, 1 gets mapped to the point at 2, 1 after doing all 3 of those transformations. And that matches one of the vertices that we see over here. Okay, similarly, seeing what happens to the vertex that was at 3, 1, that's this point over here. After multiplying this matrix, the homogeneous coordinates gets mapped to 2, 7, 1. So that's going to get mapped to a point that has coordinates 2, 7, which is the point over here. And then for the very last vertex, the one over here at 2, 3, we can see indeed it gets mapped to minus 4, 4 over here. So we could just take this black triangle and map it straight to this green triangle by multiplying by the product of those 3 transformations. And so if you are interested in playing around with these maps in Python and generating these figures and seeing what happens when you compose different types of transformations, I put a link to the Google Colab doc where I created these figures down below in the description of this video and the previous videos if you want to view that document and play around with some of these transformations.